Hello everyone, this is my ENR 3700 final project, and I'm looking at groundwater recharge potential on abandoned mining lands in Muskingum County, Ohio. So here on the right, I have a picture of a mining site in Muskingum County. This is taken around 1980. The machine pictured there is named Big Muskie, and it's the largest dragline ever built in the entire world. So if you don't know what a dragline is, it's essentially an excavator, just a really big excavator. And I think that this picture provides good context to how important mining used to be in Muskingum County. Yeah, so just a little bit about me. I'm studying hydrogeology, so I'm interested in soils and groundwater and things of that nature. And the content of this project was mostly influenced by a project I did in an environmental policy class that was about abandoned mine reclamation and acid mine drainage. So basically, I'm just combining my interests here because I find disturbed land, like mining land, really interesting to learn about, especially in the context of hydrogeology. All right, so we are focusing on Muskingum County, which is just east of the center of Ohio here in this Appalachian region. So this entire region, but specifically Muskingum County, was really important for coal extraction up until the early 2000s, when we started transitioning off of coal onto oil and natural gas. But these mining lands that you can see pictured here have been mostly left in the same condition. So this is classified as barren land since there is no vegetation and highly disturbed soil. I mean, you can see there is just nothing there. So, I mean, imagine hundreds of these sites just left open like this. So I was interested in seeing how this land affects groundwater recharge. And here's just a simple graphic that demonstrates how groundwater recharge works. It's essentially these underground water storage areas that are called aquifers and how quickly the water within them is replenished. Water is usually extracted from these aquifers for use in agriculture, industry, and for drinking water. There's a lot of factors that can affect recharge, but slopes, vegetation, and soil type are a few that usually make mining land interesting because it's usually steeply sloped where they extracted, and there's usually not any vegetation, and the soil is always highly disturbed. So I used quite a few data sets to cover these factors that I just mentioned. Some of them were directly from ArcGIS online users, like this map of Muskingum County and the abandoned mines layer, but these other ones I downloaded and moved them in from external websites. And here's an example of this land cover one. This one was from the National Land Cover Database website. I then had to use the clip tool to make all of the data sets the same shape as Muskingum County. And then I used the terrain and elevation map that I downloaded, and I used that to calculate the slope in each cell in this data set. So I inputted this terrain layer into the slope tool, and it just automatically calculates the steepness of the terrain surface for every cell in this map, and it gives me like a new raster layer for that. These values that it gave me represent the slope in degrees, which, yeah. Now, the main thing I wanted to do is see how groundwater recharge is affected and if it's affected by any of this. So to do this, I created a ranking system for the different factors that affect groundwater recharge. The scale is 1 to 4, with 1 being very poor and 4 being very good. So you can see it's on each of the tables here. And groundwater recharge is generally classified by these 3 metrics, but I decided where the cutoffs were for each classification. Obviously not on my own, but with the help of these studies I listed over here. Most of these are case studies that are similar to what I'm doing here. And so after ranking all these characteristics, I used the reclassify tool for each layer, and I defined it by the new ranking system. And here you can see just an example of a reclassified layer. This is the slope layer. So if you'll remember the slope layer that I pulled up earlier in this presentation, now it looks like this, and it's reclassified by the new recharge potential values. So with my new reclassified layers, I used the raster calculator to simply add them together. So I took all of these new raster layers that I made reclassified by recharge, and I just added them together using this equation. Each factor is an equal weight because it's just simple addition. And then this produced a separate layer that was these all combined, which you will see in my results slide. And because this is an unweighted addition, the values go up to 12. And then this is another table where I reclassified the recharge potential based on the values of this new layer. So finally, I needed to compare the entire county's recharge potential with that of abandoned mining lands. So you can see here, these are my abandoned mining lands outlined in pink. I used the zonal statistics as table tool to find any correlation between the mining lands and groundwater recharge potential. Essentially, I input this mining layer and use the mine code as the zonal ID. Since it's unique to this layer, I knew the entire county wasn't going to have the mine code attribute, so that makes it different from the county layer. And then I wanted to find the mean recharge potential of the mining areas, and this tool spat out a table for me to use. And to compare the mean to the rest of the county, I did the same process, but I used the county outline as my zone. So finally, here are my results. Just at a glance, you can see the majority of the county is red and orange. So the entire county had relatively low mean groundwater recharge potential. However, these areas that are inside the abandoned mining land, they have even lower groundwater recharge potential. You can kind of tell on this map, I wish it was a little bit bigger, but the areas inside these mining lands are mostly red, and so it's more concentrated inside these mining lands. And by the way, the white areas are all bodies of water, so they don't count in this recharge. Here are the actual numbers. So you'll see that the abandoned mining land has a mean groundwater recharge potential value of 1.6, and then Muskingum County as a whole has a mean groundwater recharge potential value of 1.8. So not a huge difference, but it is definitely lower where there is mining land. So these results align with what is already known about the impact of mining on soils and their hydrologic function. So mining frequently compacts soils, alters subsurface structure, and removes vegetation. I mean, if you remember the pictures earlier of mining sites in Muskingum County, there's just no vegetation there. And all of those things reduce infiltration capacity and percolation, which are the main processes of groundwater recharge. And because my analysis equally weighted slope, land cover, and soil hydrologic group, the consistently low average recharge values within the mining areas indicate that those factors may have been degraded in ways that inhibit recharge, which is what I thought in the first place. But much of the abandoned mining land in Muskingum County already corresponds to hydrologic soil groups C and D, which have naturally poor infiltration because of like finer textures or compaction, but many of the mining areas also lack land cover types like wetlands or grasslands that are good at infiltrating water. They instead, like I've said before, reflect barren land cover types, which I did classify as very poor for recharge. Combined with steeper slopes in these areas, these factors explain why the mean recharge potential in mining lands is lower than the county mean. The implications of this are really important for water resource management. So in regions that have extensive historical mining, low groundwater recharge means these landscapes recover water slowly after extracting the water or after a drought. So this means that like groundwater dependent ecosystems or communities are probably going to face long-term water limitations. So in Muskingum County, this can inform decisions about where future groundwater withdrawal should occur and what areas may need reclamation. For example, abandoned mine lands with very poor recharge potential may be bad candidates to like put a development of houses on, but it could be prioritized for reclamation practices such as reforestation, soil decompaction, or wetland restoration. And here are all of my sources. Thank you for listening.